Hey guys, welcome back. So this is the first lesson we're going to use the Galapagos component. And before we can do that, we need to have an actual input for the Galapagos component. And that's going to be a component called evaluate surface. And that component will help us to extract a point which we can evaluate for its z value. So let's double click on the canvas and type in evaluate surface. This one. And let's connect our surface to the S. And for the UV, we need to specify a XY point. So let's go to the Vector tab and let's go to Construct Point. And let's double click on the canvas and let's insert two number sliders. And let's double click on the slider and let's set the accuracy or the digits to 5. So we have a little bit more accuracy. And let's copy it over. Nice. So now let's connect the point to the UV. But because the surface domain is from 0 to 100 and our point is only from 0 to 1, you can see that if I put it to its maximum, which is 1, 1, you see that it only reaches until here. But we want it to reach all the way over to the other side of the surface. Now there's a neat trick you can do, and that's called reparameterize the surface. And you can do that by right-clicking on the S and selecting reparameterize. And now as you can see, our point got all the way to the right top, which reaches all the way to the surface. And now with these two sliders, I can basically get any point I want on the surface. And that's basically what we want to achieve in the end. So those two sliders are going to be our input for our Galapagos to evaluate, our two variables, let's say. And the only thing we need to do is to find a value to optimize, and that's going to be the z value from the evaluate point component. And we're going to extract the z value by inserting another component called deconstruct point, which is located here. So let me insert a panel so we can see that value a little bit better. So now that this value is 2.8. And if I move the sliders a little bit, you see the value changing. Nice. So now it's time to start inserting our Galapagos. So you can find Galapagos under the Params tab and then under Utility. And it's here, called Galapagos. So it's a small component, it only has two inputs. One is genome and one is fitness. So for our genome, that's basically the set of variables we want to adjust. And the fitness is the fitness value you want to optimize. So as I explained previously, our two sliders are going to be our genome and the z value is going to be our fitness value. So you can basically drag from the genome to your slider and it will snap to the specific slider and simply release it. And now you see that one of the sliders got connected. To connect the other slider, simply hold your shift key, drag and connect again. And now you see that both sliders got connected. To get the z value into the Galapagos component is basically the same. You hover and drag from the fitness output to the z output from the deconstruct point component. And that's it. So now we're all set to start adjusting the settings from Galapagos. So to do that, you double click on the Galapagos logo and a new window will pop up. And this is the Galapagos editor. Here we're going to set all our settings we're going to use to run the simulation. Now I'll start at the top. So you have first a fitness value, which you can either set to maximize, to minimize, or set a specific value you want to optimize. In our case, we're going to maximize our value because we want to have the highest peak in this landscape. So we're going to leave this one at maximize. There's also a threshold input. And here you can specify an acceptable fitness value. So let's say you want to maximize for a certain amount, let's say 50. Here you can specify a threshold. So if that threshold is reached, it will actually cancel the simulation early. And then below it, there's a runtime limit, which you can enable if you want to, because some simulations, they can take days. So if you have done some test simulations and you find out that it takes a long time, you can specify a limit. And below are two solvers. The first one is our evolutionary solver, which is the one we're going to use. And below it is the annealing solver, which is another type of solving, but we're not going to use that one. We're going to be mainly preoccupied with the evolutionary solver and the settings. So max stagnant means how many of the different genomes will stay stagnant during an iteration, which means that it's a way of specifying that an optimum is reached. If a new iteration comes, let's say, and there's not a lot of difference between the previous one, which means it's stagnant. So if that happens with this amount, the simulation will stop. The population means how many different genomes are used for an iteration, which is in our case 50, which is fine. And the initial boost is basically for the first run, depending on how many variables you use, you want to use a wide net of different combinations to find already some local optima. You can kind of guesstimate this more or less, looking at what you're optimizing. If you can directly tell what your values more or less will be, you can lower this number, like in our simple example, but later on we're going to use a more higher example. So for now, I think 2 is fine. Oh well, let's increase a little bit to 4. Maintain means the percentage of genomes that are fit enough to pass to the next generation, which is in our case is 5, which is fine. And then we come to the last setting, which is inbreeding, and that is also one of the most interesting settings. So inbreeding is an interesting factor, and it allows a number between -100 and 100. -100 meaning completely zoophilic, and 100 meaning completely incestuous. Some fit enough genomes get selected for mating and reproducing another set of genomes for the next generations. Depending on the distance to their neighboring genomes, this can either be incestuous, which means only very close related genomes get selected, which in return results in offspring that is very similar to the two parents, or zoophilic, which means two genomes with a large distance between them to mate, resulting in offspring that is more diverse. Depending on how obvious the optimum you're trying to reach is, you might choose a percentage. In our example case, the standard 75% incestuous is okay, as not a lot of variables are in play. And also only one variable gets optimized, which is the z-value of our surface. You can find more information about evolutionary solving on Daniel Rutten's blog, which the links are located on the right side of the solver. So let's go to our solver tab, which is located here. And here's basically where the solving happens. So on the left, we have the evolutionary solver selected. The right one is the annealing solver, but we're not going to use that one. So to the right of that one, there's the start button. So we can start the solver. And on the left, we have the speed of which it will solve. We're going to set it to the slowest one, so we can actually see what's happening in the Rhino display. If you set it to the fastest, it will not update the viewport, but it will run way faster, which we're going to use later on. But for now, let's switch it to the slowest one. And let's hit OK. Before we run it, let's visualize our point in our surface a little bit better, so we can see a little bit better what's going on. So let's insert a point component. And let's draw the wireframe of our surface. Let's set this number high to 5. Nice. So let's color these lines a little bit different. Use a color swatch. Set it to white. That's fine. And let's color also our point. And let's give it a blue color. So it pops out a little bit more. Nice. So let's fire up Galapagos by double-clicking on the component again. So all the settings are set. So let's go to our solver and let's switch it to our slowest one so we can see what's going on. And let's hit Start Solver. So as you can see now in the Rhino canvas, you see the blue dot jumping around the surface like crazy. And on the Galapagos solver, you see on the left bottom part, you see the different genomes. The genomes that are represented with an X, those are the ones that didn't make it to the next round. And the black dots are the ones that actually made it to the next round. So that's pretty nice. And on the middle part, you see the different variables being represented with a line, connected with a line. And all the way on the right side, you see the Z values. And you see it slowly being optimized towards 14 point something. I think pretty soon it's going to find the actual optimum. As you also can see in the Rhino canvas, the blue dot kind of hovers around this peak. And all the way on the top, the graph, you see the different iterations. Right now it's at 42. We can speed up this process a little bit so it doesn't take that long. So let's switch on the middle speed. So now you see that the optimization goes a little faster. So now as you can see, it stopped. So now we can reinstate the highest value, the most optimum value it found, which is 14.07. So you can simply select it and hit reinstate and hit OK. So those were the two for the X. That was the value that was most optimal, and also for the Y. And that's in a nutshell how Galapagos works and how it tries to find the optimum, let's say, by first spreading a wide net of different variations of genomes, and slowly by discarding genomes that are not fit, getting to the optimum you want to find. So this is a metaphor you can keep in your mind how an evolutionary solver works, because in the next examples, we're going to use we're going to optimize floor areas. So not a landscape, let's say, but you can use this metaphor as in the back of your mind to always figure out like, okay, this is how an evolutionary solver works. So next lesson, we're going to jump into our next example, which is a real-life scenario where we're going to optimize a certain set of plots and try to equalize their floor areas. So please stick around.